Welcome to the Math 030 Pre-Calc Clinic Unit 3 test review. The first problem that you'll see on this test is number 1, and it deals with even versus odd functions. So in order to be an even function, graphically you're symmetric about the y-axis, and if you're odd, you're symmetric about the origin. If you're an even function or an odd function, the way that you can test algebraically is you plug in negative x, so we find f of negative x, and then if out pops out like the same original function, f of x, your function was even. If out pops the opposite function, so all terms are the opposite, then it's an odd function. If neither of those things occurs, then it's neither even nor odd. So let's look at A and B. We want to find, these are algebraic, so we're going to use this, and we want to find f of negative x. So we're going to plug in negative x, I'll do that in white. All right, when we plug in negative x, we'll plug it in here, raise it to the fourth. We'll plug it in here, raise it to the third, and it doesn't get plugged in here. Now, when we take a negative value to an even power, like the fourth power, it doesn't matter that it was negative. It ends up just being what x to the fourth was. So the negative 3 stays, and it just stays as x to the fourth. However, if we take a negative number and raise it to the third power, it becomes a negative output. So this is going to end up being a minus 2x cubed here. And minus 1. All right, so that is what f of negative x was. We want to see, is f of negative x the same as the original f of x? Then it would mean it would be even. It's not. The first term's the same, but the second term's opposite, and the last term's the same. It's not even. Is it all opposite, meaning is every single term opposite? No. The first term's the same. The only opposite term is the middle term. So part A is neither even nor odd. So this is neither. We can also see that this function has qualities of both even exponent and an odd exponent together, therefore it's going to be neither. In part B, let's again find f of negative x and see how it compares to f of x. So we're raising negative x now to the fifth and negative x now to the third. This ends up becoming negative x to the fifth since it's raising to an odd. Then whenever we raise a negative to an odd, it becomes a negative that out front, so that would end up being a plus 2x cubed. All right, so this is what f of negative x was. It clearly is not the exact same as the original, but it is the exact opposite of the original f of x. Right here, this is negative f of x. Negative f of x means everything has been multiplied through by a negative, basically. So f of x was a positive first term here and a negative second term here. And then it was distributed through by a negative sign. The first term turned opposite, so did the second term from the original. So f of negative x equals negative f of x. That's an odd characteristic. We can also see that both of the exponents are odd. So part B is an odd function. The second problem on your test deals with the Pythagorean theorem, and we remember the Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs. So a and b would be 10 and x in either order, and c is the hypotenuse. In this case, c is 17. So we're looking for x, which we can call a or b, either one. So filling in, I'll just call x a. Plus 10 squared equals 17 squared. So then we'll have x squared plus 100 equals 289. Minus 100 will be 189. And then when we take the square root, we have to see if we can break down 189. And 189 is actually divisible by 9. 9 is the biggest perfect square factor, and I had to pause and use my calculator to see. 9 times 21 gives us 189. So this ends up becoming the square root of 9, which is 3 root 21. In number 3, we have to rationalize a denominator using a conjugate. Note that in the denominator we have a binomial, two terms, and it has a root in it. So we need to make that rational. So the conjugate of the denominator would be 2 root 3 plus 4. There's a whole video explaining conjugates and rationalizing the denominator. Whatever we do to the bottom, we have to do to the top. All right, I'm going to put parentheses around this yellow denominator here. Let's first work through the numerator in white. We're basically distributing this negative 5 to both of these terms. So we'll get negative 10 root 3 minus 20 when we multiply through by negative 5. Then in the denominator, we should FOIL anytime we see two binomials being multiplied. However, in this special case where we're multiplying a binomial by its conjugate, we only need to multiply the first together and the last together because the outside and the insides cancel out. That's why we end up doing this. So I will do this part in gray. So we're going to multiply the first times the first. So 2 root 3 times 2 root 3 will give us 4 root 9. Then I'm going to multiply negative 4 times positive 4 and get minus 16. All right, you're right that root 9 is a weird way to write this, so let's just keep going. We'll have negative 10 root 3 minus 20. And then in the denominator, root 9 is really 3. So this is really 4 times 3. This number is 12. So we have 12 minus 16. All right, we'll keep going down here. So we have negative 10 root 3 minus 20 all over negative 4. Now, can all three terms be simplified? Yes. I'm going to do something to get rid of the negatives too. Let's factor out a negative 10 out front. We'll be left with root 3 minus 2, plus 2. The denominator, negative 4. And negative 10 and negative 4 can both be divided by negative 2. So 2 and 5. So here's one way we can write our final answer. If you weren't a fan of all that factoring, you can multiply the 5 back through. So here's one good answer. We can multiply the 5 back through the numerator. Or this guy right here. Either way is a fine answer. Problems 5 and 6 both deal with simplifying square roots. They will be this simple. Just simplify them. So you do need to have a good understanding of what your perfect squares are. You can have them all written down somewhere. That's a good idea. All right, none of these numbers under here are perfect squares, so we have to simplify them by breaking them down. The biggest perfect square factor of 48 is actually 16. And 16 is the biggest perfect square that is a factor of 48. It fits in 3 times. 16 times 3 is 48. Then 16, we can cross it out and bring it out. It is 4. The square root of 16 is 4, and therefore we've simplified to 4 root 3. That's it. Let's look at 120. We need to think about the biggest perfect square factor of 120. The way I do this is I take a number, like this one was pretty easy. I've done it multiple times. This I don't know off the top of my head. If you take half of 120, we're at 60. And then I think about what is the perfect square closest to 60. Since we can only divide 120 by 2, we can't divide it by like any less than that really. So the perfect square that's under 60 would be 49. 49 is not a factor of 120. The next one would be 36. We could see if 36 is a factor of 120, and it's not. The next one's 25. That's not a factor. 16, 9, those both aren't factors of 120, but 4 is. So even though 4 is very small, it's the smallest one we could actually get, it's the one that's going to work for this large number of 120. 4 times 30 is 120. And a way you can check that you got the biggest one here, the biggest perfect square, is that 30 can't be broken down itself, and it can't be. All right, we're going to cross out the square root of 4, cross it out, bring it out as a 2, and we'll get 2 root 30. Okay, on to the square root of 175. Anytime you have one that ends in 25, 50, or 75, I would check 25 first and make sure that that one works. So 175 divided by 25 is 7. 25 is one of those easy ones to check just because of money. 7 has no perfect square factors, it's prime. And then we'll cross it out, bring this out as a 5, 5 root 7. And our last one is 60, the square root of 60. We first check half of 60 is 30. All right, the next perfect square under 30 is 25. 25 is not a factor. The next one would be 16. 16 is not a factor of 30. The next perfect square down would be 9. 9 is not a factor of 30. So 4, it looks like it is. 4 times 15 is in fact 60, and 15 cannot be broken down at all, so we know we picked the biggest one with 4. Cross it out, it's a 2, and we get 2 root 15. I made a mistake on the earlier slide. Simplifying the square roots is numbers 4 and 5, and this one will be number 6. All right, dealing with special right triangles means we're dealing with either a 45-45-90 or a 30-60-90. Let's first focus on the 45-45-90. So the relationship is that of a root 2. And so the legs are the same. They're congruent in a 45-45-90. And so we're not looking for the other leg. But we're looking for this leg right here, and we know the hypotenuse. So if we're given the hypotenuse, we want to divide by root 2 to find the leg length. That means we need to take 6 and divide it by root 2, and that's how we will find what A, our leg length, is. Now, we can't write our final answer as 6 over root 2 because this has an irrational denominator. So we need to rationalize the denominator by multiplying both top and bottom by root 2. So we'll get 6 root 2 over plane 2. The 6 and the 2 cancel. They can both be divided by 2. And so we'll get 3 root 2 as our A value. All right, let's say in this case we're given the leg and we want to find the hypotenuse. So if we're given the leg, we multiply by root 2 to find the hypotenuse. So C, our hypotenuse, is we take the leg and multiply it by root 2. All done. For the next special right triangle, the 30-60-90, it's a little bit more complicated because there are no two sides that are congruent, but there still is a special relationship among the three sides. The short side, the one across from the smallest angle, one across from the 30-degree angle, we'll call X. That's kind of like home base. It's what you want to get. Because it's easy to get the hypotenuse, you just double it. And then if you have the short leg X, it's easy to get the long leg, which you just multiply by root 3. So basically, if you're given the long leg or given the hypotenuse, you want to find the short leg. And if you're given the short leg, it's very easy to multiply in order to get what else you need. So let's take a look at an example. Let's say we want to find both A and C in this case. Now we're given the short leg. In order to find the long leg, we need to multiply by root 3. So A equals 6 times root 3. Done. When we're given the short leg again, 6, we multiply by 2 or double it to get the hypotenuse. So C is 12. No simplification necessary because we didn't have to divide by any roots. Let's do one more. All right, in this example, we do not know the short leg, but we want to find it. We're actually given the long leg. So when you're given the long leg, you want to divide by root 3, since their relationship is a root 3 multiple. And we want to divide by root 3 to find our little leg here, B. So B is 18 divided by root 3. Then we need to multiply the top and bottom by root 3 to rationalize. So we'll get 18 root 3 all over 3. 18 and 3 can both be divided by 3. So we'll get 6 root 3 is our short leg. That's the relationship between those special right triangles. I would just write down what I wrote down here, and then you should be fine with these problems, so long as you don't leave a root in any denominator. All right, number 8 will be translating either left, right, up, or down using the absolute value graph y equals the absolute value of x. Up in the corner, I wrote just the general ways that we move. If the plus or minus a number is on the inside of the absolute value, we're moving in the x direction, left and right. Plus does mean left and minus does mean right. Then if the plus or minus a number is on the outside of the absolute value, that means we're moving in the vertical direction, up and down, and it's like what you would think. So let's take a look at our original gray graph, absolute value of x. Then we want to translate it to become this orange function, the absolute value of x minus 3. That means that we are going to be moving 3 units to the right from the original function. So instead of the vertex at 0, 0, the vertex will now be at 3, 0. And our function shape has not changed. We're still going up the diagonals, and that is our new function. The next one will be in green. So we're again starting with our parent graph in gray. And we want to translate that, in this case, 2 units up. The plus 2 is on the outside of the absolute value. So starting with our gray, we want to not have the vertex at 0, 0, but have it at 0, 2. And then we keep our same shape. And that is that translated graph. Finally, the one in yellow has us graphing the absolute value of x plus 1. The plus 1's on the inside, and it's a plus, so that means we're going to be moving 1 unit to the left from our original graph in gray. So in yellow, I will have the vertex here at -1, 0. And that is where it will be graphed. These aren't too bad. Again, just have these rules written down or a couple examples written down so you can make sure that you are translating correctly on ALEKS. Number 10 on your Unit 3 test will ask you if the functions that are graphed are one-to-one. Remember, to be a one-to-one function, it means both the original function and that function's inverse. Well, and the function has an inverse that is also a function. So it means that our function obviously passes the vertical line test, we call it a function, but in order for its inverse to also be a function, it has to pass the horizontal line test, meaning if we graph any horizontal line or draw any horizontal line through it, it can only hit the graph at most 1 time. If it hits more than once, the function's not one-to-one. It doesn't pass the horizontal line test. Let's take a look at this first graphed function right here. I clearly can draw, and I'll draw in orange, I can draw a horizontal line and hit more than 1 time. This is not one-to-one. It's a function, but it's not a one-to-one function. Next, we have this cubic function. No matter how many horizontal lines I draw through it, I only hit at most 1 time. Therefore, yes, this function is one-to-one. And lastly, we have a parabola here. A parabola is a function, but is its inverse a function? Let's see. No. I can draw multiple horizontal lines and they hit more than 1 time. So no, this is not a one-to-one function. Problem number 11 will deal with 2 types of inverse functions. In this case, we have f of x and g of x. F of x is just 3 coordinate points. It's a function. G of x is a linear function. So it's inverse. The idea of an inverse, or this little -1 up here, means inverse. The idea of an inverse is that x and y swap. They switch spots. So if we want to find f inverse of 2, that's really saying I want to know what is the x value when y is 2 instead. It's just 1. It's going the other way. So this one's pretty easy when it's just written out like this. This would be 1. The f inverse of 6, when y is 6, what is x? X is 5. Let's now move on to finding the inverse of g of x in an algebraic way. All right, we want to find g inverse of x. The way that we're going to do that is we're going to take g of x, and I'm going to write it as y equals 5x plus 3 instead of writing g of x. Then x and y swap spots. So it's x equals 5y plus 3. Then we solve for y. To solve for y, we have to divide everything by 5. And so we can write it as x minus 3 all over 5, and that equals our new inverse function. So g inverse of x is x minus 3 all over 5. The last idea with that is that with inverses, if you compose them, find g inverse of g of x or even g of g inverse of x. If you compose them, whatever is inputted ends up being the same thing that is outputted. So if we wanted to find the composition g inverse of g of the number 3, it is just 3. It's going through something and then it's inverse, and so what ends up being inputted is the same thing that is being outputted. Problem number 13 deals with the least common denominator, or LCD. When we see that we need to find the least common denominator between two fractions, we want to first see if we can factor the denominators, and both of these are quadratic trinomials that can be factored. This first denominator can be factored into x minus 4, x plus 3, and the second one can be factored into x minus 4, x minus 12. Now we have the two denominators rewritten. Our LCD is going to be each factor written only one time. So we see that we have 4 factors, and one of them, repeats. So I'm going to write 3 factors as our LCD. So our LCD is x minus 4, x plus 3, and x minus 12. The order that we write those factors does not matter. Problems 14 and 15 deal with adding or subtracting fractions. Problem 14, I'm not going to do an explicit example because it will be when the denominators are already common, and those ones aren't too bad. But this one's going to be one where the denominators are not the same. So here's an example. Let's say we have x plus 1 all over x minus 6, and we're subtracting x minus 3 all over x. We need to find our LCD. Both of our denominators are already factored, and so one of the factors is an x and one of them is an x minus 6. So our LCD needs to be each factor written once. So it's x minus 6. X is its own factor. It needs to be written as 1. All right, so now we need to get both of these denominators to look like this. So this first one is missing the x down here. So we're going to multiply both the bottom and top by an x, and I'll put parentheses where necessary. Then in the second fraction, we need to make this denominator look like our LCD. So both the top and the bottom need to be multiplied by x minus 6. All right, our new fractions will now be written in orange. So I'm going to multiply through x times x and x times 1. So we'll have x squared plus x all over x minus 6. Then we'll subtract, and this next fraction, we're going to have to FOIL this out, so we'll have x squared minus 6x minus 3x, so minus 9x, plus 18, all over our common denominator. Now I'm glad this is a subtraction example because we do need to subtract this entire numerator when we're subtracting. We need to distribute this minus sign through. So let's write it as one single fraction. We'll do that in yellow. The denominator stays. Since it's common denominator, we can just subtract our numerators. So we'll have x squared plus x. Then this minus sign needs to be distributed through to all 3 terms. So minus x squared plus 9x minus 18. We can then see that the x squareds end up canceling. We can combine a 1x and a 9x, and we can write that over here. So we'll have 10x minus 18 all over x minus 6. And let's see if factoring the numerator can get anything to cancel. It looks like they have a GCF of 2, so we're left with 5x minus 9 all over x minus 6. Really nothing ends up canceling, like this 2 and x can't cancel at all. So this is a totally fine way to write your final answer. So is this. They're both totally great ways to write your final answer. Problems number 16 and 17 deal with complex fractions. That is fractions within a bigger fraction. So we're really dividing 2 fractions here. That's what taking a fraction is dividing 2 things. So we can rewrite this. Dividing a fraction means multiplying by the reciprocal. So our first fraction can stay the same, and that's an x to the 4th there. But then we're going to multiply by the reciprocal of this fraction. Reciprocal means flip. So we're going to multiply by this 4x cubed all over x minus 5. Then we can cross cancel. Cross canceling means top to bottom canceling in any way. So this 4 and this 12 can both be divided by 4. I'm going to write a 1 here and a 3 here. Then we see that we have an x cubed and an x to the 4th. And x cubed can be canceled. So if we cancel an x cubed up here, it's gone. And then this just becomes an x. If we cancel x cubed out of it, it becomes x to the 1st. This 5 and this 5 cannot cancel. This is x minus 5. The 5 is not just alone. All right, let's multiply across and see what we end up getting. So in our numerator, we'll have 5 times 1. In our denominator, we have 3 times x minus 5. Nothing can be simplified here, and that is our final answer. All right, in this next example with the complex fraction, we have more going on than just the ability to multiply by the reciprocal here. This one has more than one fraction in the top and the bottom. And so what we need to do is get it down to one fraction up here and one fraction down here. The way we're going to do that is just look at the numerator, and look at the denominator. Look at all the denominators, basically. 49, 7x, and x. We need to find an LCD. So out of 49 and 7, the LCD would be 49. And we need an x in there. Now, a good shortcut for this to eliminate the denominators is to just multiply through everything by the LCD. Multiply all 4 fractions through by the LCD. So we're going to multiply this fraction by 49x. We're going to multiply this fraction by 49x and the 2 down here. The idea is that the denominators end up going away and it's less complex. Let's see how that works. Let's cancel in black. So here in this first fraction multiplication, the 49 over 49 cancels. In the second one, the x and the x cancel, and then the 49 and the 7 can both be divisible by 7, so this turns just into a 7 here instead of a 49. In the denominator down here, again, the 49s cancel. They're both technically divisible by 49. They become 1s. Then in our second fraction, just the x's cancel. All right, I'm going to rewrite what we have down here. There's our giant fraction bar in the middle. This first fraction here becomes x times 8. No more denominator. So that's an 8x. The second fraction, or the second one, becomes minus 8 times 7. So minus 56. In our denominator, we see that we have an x times an x, so that's x squared. Then we have minus 1 times 49. Now, as somebody who's been working in ALEKS for a while now, you should see, hey, these are both factorable top and bottom here. So let's factor over here in white. In the numerator, we can factor out a GCF of 8, and we'll be left with x minus 7. Our denominator is a difference of squares, and it factors as x plus 7, x minus 7. We can then see that the x minus 7 factors can cancel, and we're left with 8 over x plus 7. Number 19 is a very simple problem. So the simplest ones, really make sure that you got it right because they're the easiest way to get some points. All right, when we have two factors or more than that equal to 0, all we need to do is set each factor equal to 0. So 8 plus y is a factor and 3y minus 7 is a factor. So we're going to set 8 plus y to 0, and then we're going to set 3y minus 7 equal to 0. And when we solve for y here, we'll get that y is negative 8. That's one solution. Over here, we will add 7. And then our second step will be to divide by 3. So we see that our two solutions when we solve are negative 8 and 7/3. On ALEKS, you definitely need to make sure they're separated by a comma, but that's really the gist of it. This one is not too bad. All right, number 20 is having us solve a quadratic where a is greater than 1. What you need to do in order to solve a quadratic is get it equal to 0, preferably keeping the quadratic term positive. So I'm going to add 8x and add 3 first. So we'll have 4x squared plus 8x plus 3, and now it's equal to 0. Now it's ready to either factor if it can be factored, or you can always use the quadratic formula, which will work no matter what. So it's completely up to you. I'm going to see if this is factorable first. So we got to multiply a times c, we get 12. Are there two numbers that multiply to 12 that add up to 8? Our b value, yes, this is factorable. We could use 6 and 2. So it is factorable. I encourage you though, if you're not a big fan of factoring, especially when a is not 1, that you are free to use the quadratic formula and you still will get solutions if it does have solutions. So I'm going to factor it. So we'll get 4 terms, 4x squared, and then the plus 3, those stay. Then we split the 8x into plus 6x and plus 2x. And then we factor by grouping. First group, second group. The GCF of the first group is 2x. We're left with 2x plus 3. The GCF of the second group is 1 plus 1, so we're left with 2x plus 3. What's inside those parentheses needs to be the same. One parenthesis ends up being the stuff on the outside, the 2x and the plus 1. The other parenthesis is 2x plus 3, the stuff on the inside, equals 0. Now, from here, if you wanted to double check that you did this right, you could multiply this back out through foiling and make sure you got back out to either here, FOIL, or here when you combine the 6 and the 2x. All right, then we set each factor to 0. So we set 2x plus 1 equal to 0, and we set 2x plus 3 equal to 0 and solve. So we'll subtract 1 and divide by 2. So negative 1/2 is a solution. Here we'll subtract 3 and divide by 2. So negative 3/2 is our other solution. A good way to check too is if you put this function into your calculator, it should hit the x-axis here and here. All right, that's really it for the Unit 3 test. Best of luck.